All right, everybody, welcome to Artificial Intelligence. I've had about 75% of you or so in class before. For those of you that haven't, I'm Dr. Ferrer. I'll be your tour guide to AI this semester. Go over some details of logistics. My office is the last office on the left in this third floor hallway. So if you come up the stairs and turn left, last door on the left, right next to that Windows lab, that's my office. If you come up the elevator and turn right, again, last door on the left, that'll be my office. So, cool. So in this class, we're going to take an introductory look at lots of different algorithms and data structures that fall generally under the heading of artificial intelligence. It's an extremely broad topic. Lots and lots of work has been done in this area. We are just going to be doing the lightest sampling of it this semester. So a lot of what I want to achieve with you all this semester, I've actually expressed these last two learning goals here. Our projects are going to heavily emphasize conducting experiments to get a feel for how well a particular technique works in a specific domain or for a specific purpose. And I want you also to be thinking about, in general, what is the scientific basis for claims about artificial intelligence? There's a tremendous amount of hype associated with AI. Some of it is justified. Some of it is not. And we're going to spend some time this semester trying to tease out some of those distinctions. So there's plenty of seats in the front. It's all right. There are a couple in the middle row there too. So anyway, for office hours, I just make use of BookMe. So I don't have any set hours, but you can just go ahead, make an appointment, and it'll appear on my calendar, and I'll be waiting for you there. Class webpage here. It also serves as the syllabus. You can access this directly via Moodle. So I'll be using Moodle both as a repository of course information and, extremely importantly, as the means by which you will submit your assignments. And then I will be keeping your grades in Moodle, and you'll be able to check your grades and so forth. I don't require a textbook for this class. I'll go over during class whatever you need to know. But often people like having a book and having a resource. If you do, I recommend this one, Artificial Intelligence, A Modern Approach. It's kind of the standard textbook for this topic. The main reason I don't require it is that book contains about enough material for maybe 8 semesters of a course. I mean, it's a veritable AI encyclopedia. It's kind of fun to read. It's kind of fun to have. But in the more distant past, when I look and found myself covering maybe, 8 sections out of the hundreds that are in it, it just didn't seem like a very cost-effective ask for students. So I suggested if you want a book and you want to have that extra resource, it's a great resource, but I certainly am in this class. So, grading. There are 1,000 points available this semester, and here are thresholds for the grades that you presumably are interested in. So clear 900 points, you get an A, and so on down there. Where does your grade come from? This is a total project course. There are no exams, but there are a lot of projects. So you're going to be working pretty hard this semester in this class, and that's the means by which we're going to learn an awful lot. So there are going to be 9 major projects plus a free-form final project. You'll have basically a week for each of these projects off in between. We're going to be at a pace in order to learn as much as we can this semester. Fascinating subject. A major purpose of the final project, which as you can see is worth nearly a quarter of your final grade, is to give you all an opportunity to study or explore an area of artificial intelligence that we didn't necessarily cover elsewhere in the course. Like I mentioned, this is a huge topic. There are lots and lots of areas that we'll be barely touching on this semester, if at all. And if there's some particular area where you really feel like, I want to do a deep dive into that topic, the final project is an opportunity for you to do that. And so something to look forward to. We're not going to really think much about final projects until after spring break. So the week after spring break, you'll be deciding your project topics and you'll start working on it there at roughly that point. So programming projects. So you're going to develop your understanding of AI by developing software that uses AI algorithms to achieve goals in some kind of a domain. And you'll be largely implementing these algorithms and data structures yourself. These assignments are all in the Java programming language. And in general, I'm going to be giving you a pretty substantial skeleton for each assignment with specific methods for you to implement. In many cases, it'll be a combination of, here's an algorithm I went over in class, code it up, and now do the following creative things with it, or do the following kind of creative extensions with it, or what have you. That's going to be the general flavor that these assignments have. Each assignment is going to take place over 3 class periods. So there'll be a class period where I go over the concepts for the assignment. The next class period, I'm going to have you all do some very brief progress reports on how it's coming. And then in the third class period, each of you is going to do a presentation about how it went. And there are a lot of you, and so what I'm thinking about doing is have you do the presentations in pairs. So in other words, you'll each do the assignments on your own, but then meet up with your partner and kind of do a joint presentation about what each of you learned, similarities, differences, and so forth. And I think that'll help expedite things a bit. So yeah, this class is about twice as big than the last time I taught it, which is great. That's wonderful, but it takes a little adjusting, and that's okay. All right, so for each project, you can earn up to 85 points. 25 points will be getting the programming right. 20 points will be doing the experiments that you're assigned to do for that assignment. 5 points will be for a progress report. 25 points will be writing a paper describing the results of what you did. This class actually carries a W-2 credit due to the volume of writing that we do. So with each of the 9 projects having a paper and then the final project being a long paper, you're going to get some fairly good writing practice actually in this class. And then the final presentation, I'll be looking for a 3-slide PowerPoint going over the results of your paper, and that'll be worth 10 points. Put it together, that's essentially the rubric for each assignment. And then each individual assignment will have it broken down in more detail as well, so that you know exactly what you need to do to earn the credit for it. Projects are returned. You're welcome to revise and resubmit your work. I will grade anew each submitted revision and average the original and revised grades to produce a new grade for the assignment. Revisions may be submitted anytime up to the start of the final exam period. So I don't take any late work, but you're welcome to revise nothing and get half credit. So sometimes it just needs to happen. So, but for your own sake, I would suggest keeping it rare. There you are. And let's see, did I miss anything? Yeah, final exam period. So final exam period for this class is Thursday, May 7th, 8:30 to 11:30 a.m. You're going to be presenting your final projects during that time. I like to have this on the syllabus straight out so that whatever travel arrangements or plane reservations you need to make happen after that. That's the idea. So here's our schedule this semester. So I'm going to give kind of a high-level overview of what we're going to be hitting and the directions we're going this semester. So we are going to kick things off today going over search algorithms. Then project 1 will be due a week from today, and we'll be going over details of that later in this class period. Next, we're going to study adversarial search, by which I mean board games. So AIs for games. Specifically this semester, we're going to study checkers. I think you're going to find that you can put together a very, very respectable checkers AI in the time you'll have for that project. Past years, we actually did chess, and we found we did not really have enough time to put together a respectable AI. Checkers seems to work out a little bit better. If you're really into chess, I personally kind of am. That can be a great final project topic, though. Chess is a pretty intense game. At that point, we're going to begin studying machine learning, and we're going to start with a couple of very, very simple machine learning algorithms, k-nearest neighbor and naive Bayesian classifiers. And in that week, we're going to be studying the application area of what's called sentiment analysis. And we'll go over that in more detail at that point. But the idea is, given some words, can you have it figure out whether the words express somebody feeling good about something or feeling bad about it? And we're going to be using a neat data set, which is taken from Twitter. It's a giant archive of Twitter tweets we'll be using. It's a pretty standard data set for that. Then we're going to spend a couple of weeks going over neural networks. Pretty fun concept, very, very important. And we're going to be applying two different types of neural networks to problems in handwriting recognition. And we're going to have a lot of fun with that. Then we're going to do some work on automated reasoning. So the idea here is to take some real-world domain, model it in logic, and then try to have it prove theorems about it or draw conclusions. Then we'll hit spring break. After spring break, we're going to study what's called Q-learning, which is a form of what's known as reinforcement learning, a chance for an agent to learn from experience. We're going to have a little simulated robot exploring around that will be trying to get to learn from its experiences. Then this week, we're going to hit very, very important set of machine learning algorithms, decision trees and random forests, which are widely used in a lot of applications. And we're going to kind of go back and re-examine the handwriting and the sentiment analysis using those concepts. Then the last big major assignment we're going to have is each of you is going to build a chatbot. So it's often said one of the big target problems in AI is to build a system that's so good at talking that it can fool a human. It's often been formalized as the infamous Turing test. And so for our 9th and final project this semester, the idea is based on what we've gone over throughout the semester and based on some other ideas that I'll be covering at that point, we're going to try to see out of you all who can fool the human the longest. And that'll be a way to kind of bring to the fore whatever systems you found interesting, and I think will provide an entertaining conclusion to the semester. And then you'll present your final projects then, and that will be a semester. We're going to cover a lot. You're going to learn a lot. I think you're really going to have a lot of fun. But the work is going to be kind of intense, right? Every time we start a project, you've got a week to get it done, and you're going to have to make sure to start early and prioritize it because these projects are a lot of work. Not only are you doing some coding, you're going to do some experimenting, you're going to prepare some presentations, you're going to do some writing. So you're going to have to pace yourself pretty carefully to make sure you get all that lined up. But then between projects, you get a bit of a breather in this class. Cool. Any questions on the syllabus? All right. Well, let's get started. Oops. No, go away. Okay, there, good. Okay. So to start with, we're going to think about the concept of a search algorithm. And to some degree, this will be reviewed, but we're going to go over some things that are probably new to you as well. When we talk about a search algorithm, what we're getting at is an aspect of intelligence that I think is very, very important and inspired a lot of early work in AI in particular. What I'm getting at is this. Much of intelligent behavior seems to be the product of a process of deliberation in which a mind considers different alternatives and determines based on which alternatives, according to some criteria, working out from those alternatives, the way forward, the right thing to do. So as it happens, in some ways, computers are really, really bad at this. And what I mean by that is, as a human, when we consider alternatives to things, yeah, we tend to think about 2 or 3 or whatever and kind of go with our gut a lot of the time, that sort of a thing. This is not that. What we're really going to be looking at here is imagining some kind of a puzzle to solve and coming up with some kind of systematic way of exploring all innumerable possibilities associated with it. Who's taken theory of computation or algorithms? When I say all possible combinations, what kind of red flags do you immediately notice? Yeah. Well, like a screaming red flag, isn't it? Yeah. Search algorithms are often used to attempt to come up with solutions to computationally intractable problems. Oh well, here we are. Yeah, in all seriousness, in our first assignment, we will, in fact, be trying to solve a computationally intractable problem. It'll just have a relatively small problem size, which is what's going to make it tractable for our purposes. We'll get to the details of that in a little while. A lot of early work in AI actually preceded a lot of the work done in theoretical computer science to establish the notions of intractability. To give you a feel for the timetable, does anybody know off the top of their heads when the first work was done to prove the existence of this NP-complete category of problems? A term you may have vaguely heard in algorithms or theory of computation. No idea? It was 1970, as a matter of fact. 2 years before I was born. Now, anybody know when the earliest AI work happened? Any wild guesses? Correct. About 1957, as a matter of fact. So these guys were working on some AI problems back in the 50s, and they didn't really have our modern notions of computational intractability. So they started building these search algorithms to try to solve various kinds of problems, and they developed these intuitions that, you know what, this worked great for this small problem. I'm sure scaling it is not an issue. And then Cook came along in 1970. He came up with the notion of NP completeness. And here we had early AI. And when these met, we had trouble. So a lot of work in AI ever since then has been to figure out how to recover from some of these early problems. Nevertheless, some really great concepts emerged in this time frame. And in this assignment, we're going to spend some time exploring what they involve and what they look like. This first bit is going to be a bit of review, but it's going to set the stage importantly for what we're going to be exploring. So, review. So, 2 search algorithms that may be familiar to you all. One of them is breadth first search. The other is depth first search. Either of these ring a bell for anybody? Sound familiar? Okay. Somebody explain to me what the breadth first search algorithm is. Saw a lot of nodding heads, so somebody out there can explain. Any volunteers? Yeah.
I'm going to take a complete guess.
Go for it.
If you're searching a tree, you go row to row instead of going down the branches.
Yep, that's correct. So let's review what Dan is saying. In a breadth first search problem, you've got some notion of a starting state, which we always designate with circles because that's what we do. We're building a graph, basically. And there are successors, ways we can change that state. So you do some kind of an action, you cause that state to change, and now here are 2 possibilities. With breadth first search, the way you explore the possibilities is you consider first every possibility you can reach with one action before you consider any possibility that you might reach with two actions. So here we have our start, and over here we have one action, and then here we have two actions. Thinking of things in terms of a state and actions, I think, can immediately give kind of an AI feel to this process. That is, we're imagining some entity that has some means of sensing the world and changing it in some fashion. And so what we envision is some capacity for this AI to imagine or visualize how undertaking a particular course of action can change the world. So, if breadth first search looks like that, any thoughts about what depth first search involves? Pretty loaded question. Volunteers, depth first. Yes. That's correct. Depth first search involves picking one sequence of actions until either some kind of goal is achieved, great, or some kind of disaster strikes, not great. If a disaster strikes, depth first search does what is called backtracking. It goes back up a level and then tries something else, so forth. So, just off the tops of your heads, what pros and cons might you imagine between breadth first and depth first search? What's good about breadth first as opposed to depth first? What's bad about them? What thoughts do you all have? Yeah, Dan.
Breadth first is kind of nearsighted.
Nearsighted in what way?
Well, if you were like trying to get out of a maze or something, it's not looking at a very big radius around it, whereas a depth first would be looking further ahead before it made a decision.
True. So that does accurately describe what would happen, and the idea of a maze is a really great thing to bring up, considering that it's going to be our first assignment. Actually, we're going to be using this to get out of a maze. It was as if Dan had some precognition going on here. So that's true as far as it goes, right? Breadth first search can just sort of spend a lot of time twiddling its thumbs before it gets anywhere. A depth first search, if it gets lucky, can charge ahead and nail the solution right there. So that's true. Let's flip it around. In what ways might this breadth first approach be beneficial? Yes, Fish.
Breadth first search as opposed to depth first search will find a better solution. So depth first search might find a solution, but it may not find the best solution.
That's correct. Because breadth first search looks at everything with one action before anything with two. Whatever solution it finds is guaranteed to use the minimum number of actions. Again, of course, our computational intractability red flags are going off. But it's an important property. With depth first search, it might do less work to get there, but even when it finds something, it still might not be a particularly short solution. So that's kind of a point for breadth first. A point for depth first is it might get there faster. Of course, it might not. There's like a lot of luck there. One other huge distinction between them that winds up mattering a lot. Actually, I'll just tell you what that is. Here's how we can think about it. Breadth first search uses a lot more memory, right? Because it's hanging on to everything. With depth first search, once you backtrack, you can just get rid of whatever you were looking at. So depth first search tends to use linear space, right? It just needs as much space as it needs to get to the bottom of the search tree. Whereas breadth first search, why this can use exponential space. That's kind of scary. Both of these are examples of what is called uninformed search. These are uninformed search algorithms. What we mean by uninformed search is that they do not incorporate any information about the problem domain to help navigate the search space. Instead, they are veritably robotic, mindless strategies, right? Breadth first just kind of marches through everything with 1, everything with 2, everything with 3, everything with 4. Depth first is kind of like the crazy uncle. Oh, I'm going to go all the way down here. Oh, I ran out. Okay, I got to back up. Let me try this. You know, they're each sort of insane in different ways. Before we start talking about a better approach, an informed approach, let's back up for a moment and think about a little bit of review from the data structures class. What data structure stores the candidate solutions in breadth first search?
Binary search tree.
No, not really. No. A binary search tree is more of kind of a dictionary kind of a data structure. We're going to have some much simpler. It's a real simple data structure that stores these candidates. That would be for depth first search. Right. And actually, let's think about that for a moment. If you store your candidates in a stack, essentially the way the search algorithm works is it's just a big loop that generates candidates, candidate solutions, and puts them on the stack. It comes back around and it's like, well, what am I going to look at next? So it grabs off the top of the stack the last thing you put on there. So when you consider some candidates, you push them on the stack, then you grab the last thing that you put in there. This is very depthy. So what about breadth first search? It's going to use a queue, right? First in, first out. In other words, we start here. We're now going to put in all possibilities we can generate with one action. Those go in first into the queue. Now we remove one of them, say this one. We generate possible successors. We put those into the queue. They go in the back of the queue. They're not going to be explored until everything already in there is explored. So depth first and breadth first search are effectively the same algorithm, just using a stack versus a queue. And curiously, it makes a drastic impact on how it behaves. Now, I should mention that in practice, sort of hardcore aficionados of depth first search won't necessarily maintain an explicit stack. Instead, they will just recursion their hearts out and use the call stack for the stack representation. That's what sort of intense depth first searchers will do. I want you to hang on to that thought, because when we get to adversarial search for games, we are going to be those people. Once you get into games and the like, depth first search turns out to be pretty much the only way to go. And we're going to talk about that in a couple weeks. So here, for this week, we're actually going to use breadth first as kind of our starting point, but we're going to think about how to make it better, how to use information to make it better. So thinking about using information to make it better involves introducing the notion of a heuristic estimator. Now, where am I going with this? When we're exploring a solution to a problem, and like Dan mentioned, mazes are a nice example of this, and they're so nice that that's what we're going to be studying for the next week. What we're really thinking about, right, is how far am I in the maze and how close am I to the exit? Now, imagine the following. You've got some node n, which is in my search tree, okay? And g of n is a function designating the distance from the root node to n. In other words, this is the number of steps I took from the entrance to get where I am. Okay? Now, let's imagine another little function. We're going to call this h of n. Okay? Now, we're going to have to use our imagination here because I'm about to describe a function that typically doesn't exist. So h of n represents actual distance from n to a minimum depth goal node. In other words, if there was some magical process by which one could know this is the number of steps I need to get to the end, that's the value that h of n has. And there's a technical term for this, actually, in computing. And that technical term is we would say h of n is an oracle. It's an oracle that discloses that distance. Oracles are really important theoretical constructs because oracles designate an idea of this is as good as it's going to get. So, in practice, we tend not to have oracles, but using this as a baseline gives us a conceptual framework for thinking about what we can actually achieve. So if we combine these, E of n equals G of n plus H of n. E of n is our total estimated distance from the root to a goal through some node n, okay? But now, of course, if H of n is an oracle, it's a perfect estimate. Since we don't tend to have oracles in practice, we tend to write it more like this. We say E of n equals G of n plus H prime of n. Now, H prime of n is not a first derivative or anything. Don't get the wrong idea. Mathematical types just tend to reuse notation and sometimes cause confusion. So forgive me, but this is the way it's notated typically. So this is called a heuristic estimate. In other words, we construct a guess as to the distance between where we are and where we are trying to go. And there are lots of ways that we can try to do this. Lots of simple rule of thumb kinds of techniques can be valuable in this regard. So this stuff is really abstract and probably pretty dry. So I want you to imagine with me, and in a massive personal failure, I actually left the physical device in my office today. You'll have to forgive me for this. But have you all ever seen these little puzzles that have like 8 squares and you can slide them around? Yes. 8 puzzles, they're known as. These provide a way of thinking about what we're trying to achieve here. So here's what I have in mind. Got my little puzzle, like so. And typically these have like company logos on them and that sort of thing, or little drawings or whatever. And so I'm just going to number these like so. And then this one's blank. Or when you first get it, it's got that little plastic piece to hold it in place, a little springy thing. So if you scramble this up, you could imagine using a search algorithm to find a solution, right? And the way it would find a solution is try all possible actions from a given state. where the possible actions are just essentially exchanging the blank tile for a concrete tile. It's kind of sliding it around. I can't believe I left the stupid thing in my office. I will have to bring it Thursday. Anyway, so this is known as an 8 puzzle. Now, in principle, right, you could imagine solving this with breadth first search. But boy, that sounds painful. What do we mean by painful? Well, as it happens, I have a cute little program here. And so what this program does is it represents an 8 puzzle. And I can click on a number and it'll swap with the empty, as long as it's adjacent. If it's not, I can click all day and it won't do anything. And so, I've kind of monkeyed around with it, like so. So now I want to solve it, right? So I click the solve button, and it explored 440 nodes at a depth of 9, and the solution length was 8. And then it'll show it to me, so I can click forward, and you can watch it restore it to its pristine state. This is pretty cool, okay? I can scramble it if I want, and the depth is like how many random moves it makes. So let's go with like 20. And now I'm going to solve it. At that time, it took 105,000 nodes. How deep should we go? Eric's a bad influence. Yeah. This is pretty bad too. Okay. Yeah, 462,000. Okay, let's go a little higher. And we'll solve it. I got lucky. Wait a minute. I'm going to restore it to start. All right, Eric, what'd you say? All right. Yeah, usually this is worse.
I think there's an upper limit on how.
Yeah, exactly. Yeah. So in any event, though, we can see that this really takes quite a lot of nodes. So now let me ask you all this. How might you estimate how many moves you need to make to solve it? If I just give you an arbitrary configuration, what might be some ways to estimate, to guess, how many moves you need to get to the end? It doesn't have to be perfect. It just has to be better than nothing. Any ideas?
Like a really simple one would be just like the number of slots which have the correct number.
The number of slots that have the correct number in them. So let's think about this idea for a bit. So the suggestion is actually we'll go with this. We'll go with number of incorrect tiles. Why? Because we know every incorrect tile must move, right? So that gives us an estimate. That's something we can work with. Let's check out the implications of that estimate. So out of place uses this precise estimate to figure out how much search it needs to do. So in this case, it only needed 23,000 nodes instead of 200,000. So it saved it by a factor of 10. So the beauty of this idea is if we can somehow prioritize which nodes we look at based on this total estimate, that in turn enables us to ignore really bad ideas. Not all the bad ideas, but at least some of them, right? Now, what kind of data structure could we use for our generic search algorithm to rank the possibilities according to this heuristic estimate? A priority queue. Yeah, a heap. So here's the big idea, right? We've got this heuristic estimate. So we place nodes in a min heap where they're ranked based on this combined score. That is, how far did we have to go to get to this node? And now, how many tiles are out of place? So notice that this doesn't really help with, say, intermediate moves. You know, there's often going to be situations where anything you do, you're still not going to restore something into place. But in the situations where you happen to make the move that gets you into place, those are immediately going to be preferred by the search algorithm. And it's going to focus on those sections, which is pretty cool. So this is a neat idea. This is pretty effective. It gets us somewhere. Can we do better? I mean, it was kind of a leading question. How might we do better? Here, we just observe every incorrect tile must move. Can we make any other observations about what must happen? Yes? Well, sure. Well, we know where it is, and we know where we want it to wind up. That's true. You can think of the blank. As far as this is concerned, it's just another tile. Right. Yes?
What about the correct tile? Like, maybe like keeping that in place or try to avoid once it's...
So this does have that bias as it stands, right? Because any move that would move a correct one out of place is going to be punished. Yeah.
Can we look at the distance between where tile and out of place tile is and where it needs to end up at?
Now that's an interesting idea, right? Because not only does every incorrect tile must move, they're only allowed to move one space at a time. So if we know how many spaces it has to move at minimum, that can improve our estimate, right? So as it happens, we've got that sitting here too. This is what's called the Manhattan distance. Why is it the Manhattan distance? It's like you're counting how many city blocks in Manhattan you have to travel to get there. So like this 7 needs to go 1, 2, 3. Blank needs to go 1, 2, 1, 2, 3, and so forth. So if I try to solve this with Manhattan, that took 978 nodes. So we have, by using a heuristic, reduced the number of nodes we have to look at by a factor of approximately 1,000. Not bad for a morning's work or afternoon's work. Now, this can get a lot more fun if we don't limit ourselves to the 8 puzzle. So in other words, let's go with a 4x4. Now we have a 15 puzzle. So let's go ahead and scramble at 100. This is the locking it up behavior I was looking for. I knew it had it in it. Yeah, my GUI is like totally locked up. I didn't bother to, I just wanted the shock impact. We'll come back to that. Wait, oh. Okay, we're going to re-full screen you. Okay. So, yeah, we're just going to let that go. Yeah, Ouch. So what? Okay. Have to the Manhattan distance to its desired destination. That's exactly right. Good. Okay, so let's bring some of these ideas together. This algorithm is known as best first search. It's breadth first search, but with a heap. And so by using a heap, it grabs the best node first. That is the minimum value, the root node of the heap. Okay. Now, when you implement this, I don't want you to code up your own heap. You've all taken data structures. You've earned that. Use the library heap. There's a priority queue in Java. Just use that. Okay. So best first search. Now, there are some interesting qualifiers here. Namely, there's some really interesting properties of this heuristic estimate function that greatly impact the efficacy of best first search. Here are some of those properties. Consider the following scenarios. So the first scenario says our heuristic overestimates at some point. Okay. We overestimate at some point. Our one below says we always underestimate. Our estimate is less than the oracle for all n. Here, our estimate is greater than the oracle for some n. Let's look back at the formula. What are the implications of this number being bigger than the actual distance to the end, to a goal? Does that sound like good or bad? Why bad?
Because if it's getting bigger than the goal's actual distance, then that means it's getting further away.
Yeah. So you nailed it, right? So I want you all to think about this for a minute. If you're overestimating the distance to the goal, what that means is if you think it's farther to the goal than it actually is, the search algorithm is actually going to actively avoid those paths. So that's really dangerous, right? You don't want that to happen. Underestimating, on the other hand, won't actively drive you away from a path, right? Now, there are other problems with underestimating, but in general, if we can show that we always underestimate the distance to the goal, this is what is called an admissible heuristic. So for an admissible heuristic, the estimate is always less than or equal to the actual distance to the goal. So what's nice about an admissible heuristic is that it's never going to actively reject a path that leads to the goal. In other words, with an admissible heuristic, we are able to maintain the guarantee of obtaining a minimum length path, just like breadth first search. So if we have best first search with an admissible heuristic, what we have is something that is strictly better than using breadth first search. And this combination of an admissible heuristic and best first search is called A-star search. It's called A-star search. So A-star search is a really, really important search algorithm. 99% of game AIs that are running around trying to attack your dude are using A-star. To give you a sense of the importance and the pervasiveness of this algorithm. Now, there is a different way of thinking about the notion of admissibility that can be a little easier to reason about and provide somewhat better guarantees of behavior. So you'll just have to forgive me for how all discrete mathy I'm getting, but you're gonna have to be doing a lot of forgiving this semester because we're gonna have to do this a lot. All right, so we're gonna say we've got N1 and N2. These are search nodes, okay? N2 is a successor of N1, okay? In other words, you applied some action from N1, and that produces N2, okay? Now, local admissibility, this is also known as monotonicity, is basically a way of saying you're not going to jump too far ahead. In other words, it's imaginable that you have a heuristic that doesn't overestimate the distance to the goal, but does overestimate in the middle of the search. Monotonicity excludes that possibility with the following definitions. If you're at the goal, your heuristic had, goal has an L in it, and that became a closing paren. Okay, it'll do. When you're at the goal, the estimate is 0. Then the estimate at N1 minus the estimate at N2 is less than or equal to 1. So what does this mean? Whenever you go from one successor to another, your estimate, the difference in the estimates is bounded above by 1. If it's 2 or higher, that means you're still kind of overestimating at N1, even if it's not visible beyond the overall search. As it happens, for the A puzzle, both of the heuristics we looked at were monotonic. They do not overestimate either locally or globally. And intuitively, I think that's pretty easy to see. When we think about the tiles out of place heuristic, there's no possible action you can take. You can never slide a tile such that you have put lots of tiles into place. You're only moving one thing into place at a time. Right? With the Manhattan distance, it's the same kind of idea. You're not going to teleport a tile from one square to another because you're only moving one at a time, and because we're using these Manhattan estimates, the Manhattan estimates themselves are effectively lower bounds on the number of moves that can happen. So those are monotonic heuristics. Now, admissibility isn't everything, right? For example, I could posit the following heuristic. And guess what? That's monotonic. Is it any good? What have I just done? What's that? I've said everything's the goal. In other words, I have reinvented breadth first search, right? So we need to have a way of talking about what do we actually have there, right? So here we talk about the notion of informedness. So we're going to imagine two heuristics, h prime of n and h double prime of n. So imagine the following. For all n, h prime of n is less than or equal to h double prime of n. There exists some n such that h prime of n is strictly less than h double prime of n. And for all n, h double prime of n is less than or equal to our oracle value. So that's kind of a lot of mathematical gobbledygook. Let's see what it actually means, right? So this first criterion is saying our first heuristic, h prime of n, never is bigger than h double prime of n. It's always less. The second criterion is saying there exists some n for which it's strictly less than h double prime of n. In other words, h double prime of n is giving a bigger number at some point. The third criterion is just saying h double prime of n is monotonic. So if you put all these together, what we say is h double prime of n is better informed than h prime of n. So this is a way of saying h double prime of n is a better heuristic in a rigorous way. That's what we're doing here. So what we ultimately want is the best informed heuristic we can find that's still monotonic. It won't overestimate, but it still moves us. It still gets us somewhere. So what do you all think? According to this definition, is the Manhattan distance better informed than the out of place? Using these criteria. Why, Kate? What makes the Manhattan better informed by these criteria?
Because, like, whenever you have, any time that you have a distance from just like the out of place, the distance from the Manhattan distance, like the value from the Manhattan distance is, like, better.
It's bigger, right? Yeah, really criterion 2 is very, very important here because the out of place is basically saying everything is a distance 1 away from its goal. Manhattan actually looks at that XY differential. So it'll always be less than or equal to, but given that it's possible to have to make more than one move, it's pretty easy to see, oh yeah, at some point it's going to be strictly less than. It's monotonic, and so there we are. It's a better informed heuristic. And so, right, this is the kind of theoretical result you can take to the bank, right? Because you show something like this kind of analytically, whatever experiments you do are going to be consistent with it. You're going to see a drastic reduction in the number of nodes. I wonder how breadth first search ever worked out on that thing. Oh well. Never mind it. Okay. So, okay, we're getting kind of near the end. So, We'll go to that next time. So let me go ahead and walk through with you your first assignment. So project 1 is solving mazes with A star. So we're going to have a lot of fun with this, I think. Here is the code that you'll be running. So this maze program is in a couple of different packages. There's a core package, a GUI package, and a heuristic package. In the GUI package is a program called Maze Viewer. When you run it, it looks like this. So you click on Make Maze to have it make a maze, and you can give it a width and a height. And it's got a starting location and an ending location. And you can also ask Breadth First Search to solve it. It didn't find anything because that code isn't there yet. But it will be, won't it? You can make these mazes as big as you want. So you could go by 100 by 100. Well, you know. Yeah, so you can have a lot of fun with this. But also to add some interest and also to add some computational intractability, you can add treasures to the maze. So I'm going to make a maze with a 10 by, I'm going back to 10 by 10. So this maze has 5 treasures. And so our explorer isn't considered to have completed the maze until all 5 treasures have been retrieved. So so this adds a bit of interest to the problem. By itself, the maze isn't terribly interesting. You Manhattan distance to the exit, and it generally works pretty well. But once you have the treasures in place, now you've got some interesting trade-offs to consider in terms of building some heuristics. So I think you're going to have a lot of fun with this. So that's the basic infrastructure you've got. Let me go over the other elements of what you'll be doing, and I'll show you how they fit in with this code skeleton I've given you. So you'll want to download this maze.zip. Here are some instructions to get it going in IntelliJ. So these files are in a few packages. So there is, then I've listed which classes you're going to modify are in boldface. Those are Best First Searcher and Maze Explorer. So let's look at those here in IntelliJ. So Best First Searcher is this little thing right here. So Best First Searcher, it's set up with a generic data type for the thing being searched. So a Best First object is something that can be a search node. And then it's equipped with a Best First heuristic that makes a heuristic estimate. And it's got an instance variable to indicate whether the solution is found, how deep it's gone, how many nodes it's accumulated. Updating those instance variables is important for the statistics reporting that you see on the GUI. That's how it knows. Okay. So what is implemented here is the basic pieces of breadth first search. So that algorithm I've provided. Note the presence of a queue right here. So you're going to want to study this code and understand how it produces breadth first search. Then you're going to want to replace this queue with a priority queue. It's going to be a little tricky though, because I've got this private class, the search node, okay? And so the search node is going to need to use the heuristic function to get an estimate of the distance to the goal, which will then be used by the priority queue. So there'll be a little bit of fun coding for you to do there. So that's for Best First Searcher. Then you're going to modify Maze Explorer, and that's going to be the code that deals with how a Maze Explorer becomes a Best First object. So the key idea here is to generate successors. In other words, you have to come up with an array list of Maze Explorer objects that are all places adjacent to where you currently are. So to do this, you're going to need to explore the provided code I gave you. There was no pun intended there. The maze class, maze cells, maze paths, and so forth to generate those successors. So every adjacent unblocked neighbor square. So if you look again at Maze Viewer, you'll see that the way this is set up is that when you make a maze, there are walls between cells. So unlike the maze assignment that we sometimes do in data structures, in this one, it's not that the cells are filled in, it's that there are walls between them. Okay. So every square is an open square, in effect. Now, to make this a little more interesting, you can actually decrease the perfection of your maze with the slider here. So with maximum perfection, you get what's called a perfect maze. And what we mean by a perfect maze is a maze in which there's no possibility of a cycle or a circuit. If we decrease the perfection of the maze by a little bit, then some circuits become possible. If we decrease the perfection by a lot, then a lot of circuits become possible. Now, on one level, you're probably thinking, well, boy, that looks easy. And in one sense, it is. But in another sense, it's actually harder because you've actually got more choices to make. In a perfect maze, the number of actual choices available is highly, highly constrained. As you decrease the perfection, there are more options available. And part of what you're going to be exploring in this assignment is the implications of that. How does that concretely impact your search algorithms? So, in any event, oh yeah, very, very important. Maze test. Maze test is a JUnit test case that is currently failing. Once all of the tests pass, you know that your Maze Explorer and your best first search are correct. So getting past those unit tests is going to be kind of your first obstacle to overcome. So once you've got that in place, I want you to create some of your own heuristics. Now, to create a heuristic, this is set up so that you just put the heuristic in the heuristics folder, and it will then automatically appear as a choice in the drop-down menu. So every file in this folder that implements the best first heuristic interface on a Maze Explorer will then automatically appear in the user interface as a choice. So what does this look like? It'll give you a node, which is meant to be an interior node, and then a goal node. And it's going to return an integer indicating the total distance from the starting node to the goal. Just like that. This one is breadth first search. It always returns 0. Okay. So what I'm going to be looking for you to do is you can use this as kind of a code skeleton to scaffold what you're doing. But then inside the method itself, I expect you to actually do an interesting calculation of some kind. Now, what do I have in mind? Oh, here we go. I want you to have a heuristic that some way uses Manhattan distance. That's required. 2 additional heuristics that are monotonic. Because of the treasure aspect, you can do a lot of creative stuff with Manhattan distances, right? Your first one might just be somehow uses Manhattan distance, just give me Manhattan distance to the goal. Your second one then might involve, well, how do I get the treasures in it? How do I get them involved? So you want to think about that. Then I actually want you to try to come up with some non-monotonic heuristics. In other words, try to think of ways that you might be really, really aggressive in the estimate at the cost of occasionally going a little too far. So I actually want you to play around with an idea of maybe I can get a little more information here, but it might cause some other problems in some situations. So I want you to think about those as possible. Special note, all heuristics should be completely deterministic. Any heuristic making use of random numbers will receive no credit, as a heuristic is supposed to correspond to actual information about the path to a solution. Now, you might wonder why I put that text so emphatically in there, and you probably know why. Somebody thought this was a brilliant idea in some previous iteration of the course. And it's a teaching moment, right? Because the whole point of heuristics is they need to involve actual information. If you've got random numbers in there, there's no information. You're actively destroying information. As you would imagine, these random heuristics work pretty badly. Okay. Then I've got some hints about getting the Maze Explorer and the Best First Searcher working. So I've got some detailed hints there for you to follow. And then I want some proofs in your paper. These don't have to be formal. Really just a well-constructed argument will suffice. Use this definition of monotonicity, which I've provided here. I've provided a hyperlink for it for you. Prove that your monotonic heuristics are in fact monotonic. I then want you to talk about, for each pair of them, which one's better informed. Now, it's actually possible to come up with two heuristics where neither is better informed than the other, right? One can be better in some cases than the other. So actually what would be fun to do would be to do just two of these first, do these comparisons, and if neither is better informed than the other, bam, you've got your third heuristic right there by putting them together. Just do like max of the two. So part of how you might think about going about this. And then come up with a counterexample for each of your non-monotonic heuristics to show that it does bad things. So then I want you to do some experiments. So for each heuristic, find the hardest maze it can solve in 2 minutes or less on your computer. In your paper, go ahead and note your clock speed for reference purposes. So I want you to think about hardness in terms of perfection, treasures, size of the maze. And then for each maze you generate, run each heuristic on that maze so that you don't have biases in your comparisons. And if it takes longer than 2 minutes, terminate it and record that for that experiment. It took too long. And then you can just be done with it. It diverged. So there it is. On Thursday, I'd like each of you to have a single one-slide PowerPoint, no title slide, where you just say, what do you have in mind for your heuristics? What are your ideas? So part of what we're going to do on Thursday is going to have an open discussion about what some good ideas might look like. And then submit your paper in a zip file, continue your code in a week. And there is the rubric. So we're going hurtling like crazy out the front gate. We're going to be setting a pretty rapid pace in this class. So you want to start early on these. Not a single assignment in this class is completable the night before. Yeah, Dan. Yeah. Yeah.
Is that just the left-right distance to the exit, or is that taking into account the walls?
Takes into account the walls. Yeah, yeah. So in other words, if you had a way of devising the oracle, you wouldn't even need a search algorithm. Alternatively, you could do a breadth-first search to construct your oracle. Whereupon, again, yeah. So yeah, that's why we don't actually use the oracle. Yeah. But yeah, that's what the oracle is getting you. It's getting you the distance of the best minimal path to the exit. So cool. So to start with, you want to download the code, get it all set up, read over the code base, Pummel me with questions, email, office hours, what have you. And on Thursday, we'll have some discussions about what makes some good heuristics, and we're going to talk a little bit about a couple other concepts related to all this. See you then.